Next slide. Our galaxy is a spiral galaxy that has denser parts of the disk that compress to form stars. The density enhancements form a spiral pattern in the disk. There are many stars found in between the spiral arms, but the hot luminous O and B stars make the spiral arms stand out because those hot stars don't live long enough to leave the spiral arms where they were born. The cooler, lower mass, and therefore longer-lived stars can be found anywhere in the disk, in or out of the spiral arms. Even though they make up most of the mass of the disk's stars, their light is so feeble that all you can readily see are the O and B stars, and the H2 regions around them. The O and B stars and H2 regions outline the spiral pattern the same way Christmas lights around the edges of a house will outline the borders of the house at night. This old animation of the galaxy shows that stars, with 3 example red dots, move in and out of the spiral arms because the spiral pattern rotates about half as fast as the orbital speed of the stars and gas. So where did the spiral pattern come from? Next slide. Recall the idea of differential rotation, where the stars and gas closer to the galaxy's center are able to move by greater angular amounts than stars and gas farther out from the center. That differential rotation can make a spiral pattern in a short amount of time. But differential rotation works too well because the arms should be very tightly wound up, so much that the spiral pattern would disappear after less than 1 billion years. However, we see no tightly wound galaxies, even though the galaxies are over 13 billion years old. The loose spiral arms last for billions of years. Stars move into and then out of the spiral arms. The spiral pattern rotates more slowly than the star's motion, so what maintains the spiral arms? Next slide. A spiral density wave can form in the disk that causes stars to speed up when they approach the spiral arm due to the extra gravity of the spiral arm, and the stars don't leave as quickly because they are pulled back by the extra gravity of the spiral arm. A traffic jam results. The gas clouds get compressed in the density peak of the spiral arm, which is why stars form in the spiral arms. If this idea is correct, we should see a large number of H2 regions on the downstream side of the density waves. This is observed. Another prediction of the spiral density wave theory is that the older stars will tend to make a tighter spiral pattern than the younger stars due to differential rotation, and that is also observed. A couple of other ways of making spiral arms are possible. In a process of self-propagating star formation, the shock waves from supernova explosions shape the spiral pattern. When a supernova shock wave reaches a gas cloud, it compresses the cloud to stimulate the formation of stars. Some of them will be massive enough to produce their own supernova explosions to keep the cycle going. Coupled with the differential rotation of the disk, the shock waves will keep the spiral arms visible. This process will make ragged spiral arms, the so-called flocculent spirals, like in the small nearby spiral galaxy M33. Perhaps the spiral patterns are transient, meaning that the spiral patterns come and go. This behavior is seen in computer simulations of galactic disks. It is possible that all 3 theories may be correct. Some galaxies, particularly the grand design spirals, use the density wave mechanism, and others use the self-propagating star formation or transient spiral mechanisms. Our galaxy may be an example of a spiral that uses more than one. The spiral density waves could establish the overall pattern in the disk, and the supernova explosions could modify the design somewhat. Next slide. There are 2 basic groups or populations of stars in the galaxy with very original names: Population 1 and Population 2. They are distinguished by their orbits and their metallicities, that is, how much processed gas they have made of elements heavier than helium, like carbon, oxygen, nitrogen, iron, etc., from previous generations of stars. Population 1 stars are in the disk. They have a wide range of ages from 0 to 10 billion years old. The youngest ones are in the spiral arms. Population 1 star orbits are orderly, roughly circular orbits close to the midplane of the galactic disk. Population 1 stars have higher metallicities than population 2 stars. Population 2 stars are in the stellar halo and bulge. They are old. Ages range from 10 to 13 billion years old, so they have masses less than or equal to 80% of our Sun's mass. Their orbits are much more randomly oriented than the population 1 orbits and are highly elliptical. The halo stars are metal poor with 0.001 to 0.03 times solar abundance, but the abundance increases inward toward the center. The bulge stars are metal rich, with abundances of 1 to 3 times that of the Sun. Early in the history of the galaxy, there was probably a lot of star formation and death in the bulge component, so the metal content rose quickly. The star formation rate in the disk has been more steady, so it is slowly catching up to the bulge's metal abundance. Star formation now occurs in just the disk. Next slide. As I mentioned before, the galactic center is 27,000 light-years away in the direction of the Sagittarius constellation. The dense interstellar dust layer blocks our view of the galactic center in the visible band. In the radio band, we see a strong radio source we call Sagittarius A star at the center. It is an object less than 1 parsec across. The next couple of radio band pictures zoom in by several hundred times. We see gas spiraling into a central object from a ring of neutral gas. Measurements of stellar velocities very close to the center show the stars are orbiting a compact, massive object with a mass equal to 4.5 million solar masses. Remember, if you measure orbit sizes and orbit speeds, you can then derive the mass enclosed inside the orbits. This picture shows a high-resolution infrared image of the red giants packed at the center, with the different amounts of dust producing varying amounts of reddening of the giant stars. We find that there is a large mass in a region smaller than our solar system, so it's probably a supermassive black hole with a mass about 4.5 million times that of the Sun. Just because there is a large black hole at the center does not mean that the stars in the galaxy are all orbiting around it like the planets orbit the Sun. Even if the supermassive black hole was not there, the stars would still orbit pretty much as they do now because of their mutual gravity. The mutual gravity of the stars, gas, dust, and dark matter halo hold the galaxy together. If you compare the enclosed mass inside the Sun's orbit of several hundred billion solar masses with the 4.5 million solar mass black hole, you will see that the central black hole's mass is insignificant compared to the entire galaxy. In May 2022, the Event Horizon Telescope team released an image of the shadow of the Sagittarius A star black hole. The Event Horizon Telescope used an array of 8 radio telescopes positioned across the Earth to get the resolution needed to see the details of the material around the black hole. Although the data was collected at the same time in 2017 as that collected of the supermassive black hole at the center of the giant galaxy M87, it took an additional 3 years of processing the data to produce the Sagittarius A star image than it took them to create the image of M87's black hole, which was released in 2019, because our galaxy's central black hole is about 1,000 times smaller than M87's, and therefore there are much faster changes in the light from the swirling gas. Features change in a matter of minutes instead of the days to weeks for M87's black hole.